Welcome to this video about test probe shapes. How do you choose the right probe for a reliable measurement? Pacta Industry offers this podcast with a slideshow to help you find some answers. Don't hesitate to contact the Cotelec engineers for any questions you may have about test probes.
Welcome back to the deep dive. Today, we are going to do something a little different.
We are.
Usually, we're up at the 30,000-foot view. We're talking global supply chains, massive AI models, the future of energy. But today, we are zooming in.
And I mean, really zooming in.
All the way down. We're going to the microscopic level.
It's arguably the most critical fraction of a millimeter in the entire electronics industry.
We are talking about test probe tips.
Go.
And I know what you're thinking. I can hear you right now going, wait, a metal stick that pokes a circuit board. How deep can that dive possibly be?
Right.
But let me stop you there, because I went through the documents, specifically the technical guides from Cotelec and the visual catalogs from Fine Metal, and this is not just poking stuff with a stick.
Not at all.
This is a world of spears, crowns, rolling balls, and self-cleaning claws.
It really is a geometry zoo. That's the only way to describe it. And you're right to address the skepticism early, because the biggest misconception in the industry is that these tips are just simple consumables.
Like a staple or a nail.
Exactly. You just buy a box of the sharp ones and you're good to go, right?
I think most people assume it's just a commodity. Yeah.
And that attitude costs companies millions. The source material we're looking at today explicitly calls the probe tip A, a mechanical and electrical organ.
That's a heavy term. Organ.
It is.
It implies it's alive, or at least that the system dies without it.
It sets the stakes immediately. Think about what's happening in a modern electronics factory. You have these massive, expensive test benches, millions of dollars in robotics, complex software algorithms running the show.
A whole 9 yards.
But the success of all of that, the entire assembly line, comes down to where the metal touches the target.
It's that tiny interface.
That tiny interface.
Yep.
And it has to survive thousands, maybe millions of cycles. It has to fight oxidation. It has to deal with mechanical stress. And it has to deliver a perfect electrical signal every single time.
So if that organ fails, the whole $1 million line just grinds to a halt. So our mission today is to unpack that organ. We need to understand why there are literally dozens of different shapes. Why a 30-degree cone versus a 90-degree cone? Why would you use a tip that looks like a medieval castle tower?
And what happens when you pick the wrong one?
Exactly.
And the answer to that usually involves either destroying $1 million of product or, even worse, shipping a defect that ends up in a consumer's hands.
High stakes for a tiny piece of metal.
Let's
start with the fundamental philosophy here. The source describes the probe tip as the interface between two opposing worlds. I found this fascinating.
Yeah, this is a great way to frame it. So imagine the probe tip is a diplomat standing on a border between two warring nations.
Okay.
On one side, you have the electrical world, and the electrical world is needy. It's a perfectionist.
It wants everything to be clean and predictable.
Exactly. Ideally, the electrical world wants zero resistance. It wants a pure, clean signal. It wants stability so that every time you measure, you get the exact same number. It's basically screaming, do not interrupt my current, do not give me noise.
Right. It's a sterile lab environment.
Correct. But on the other side of the border is the mechanical world. And the mechanical world is, well, it's violent.
Okay.
It's a messy factory floor. You're dealing with alignment issues. Maybe the circuit board is tilted by a micron. Maybe the conveyor belt is vibrating. You're dealing with surface attack.
Surface attack sounds aggressive.
It is. You have oxidation, dust, oil, and flux residue from the soldering process. The mechanical world says, I don't care about your perfect signal. I'm going to smash you into a dirty, rusty surface 1,000 times an hour.
So the electrical side says, touch me gently, give me a perfect signal, and the mechanical side is just, I'm going to hammer you.
Precisely. That is the paradox. The probe tip has to resolve that conflict.
Wow.
It has to be mechanically aggressive enough to survive the violence and cut through the dirt, but electrically sensitive enough to pass the signal without distortion.
And this is where the geometry comes in. The shape of the tip is the solution to that paradox.
It is. Changing the geometry changes how the probe resolves the conflict. Does it pierce? Does it slide? Does it crush? Does it scratch? The Cotelec documentation makes a really strong point here. You cannot choose a tip by feeling.
Which I assume is what happens 90% of the time.
Oh, absolutely.
Someone looks at a catalog, sees a shiny, sharp one, and says, That looks like it'll work.
That is the classic error. The text stresses looking at the real life of the workshop. You have to ignore the spec sheet for a second and look at the actual physical reality of the target.
Okay.
Is it a flat pad? Is it a via hole? Is it a pin sticking out? Because if you use a sharp spear on a delicate gold pad, you might get a great electrical connection.
On a product you just destroyed.
Exactly. You've just drilled a hole in it.
Which brings us to the catalog itself.
The geometry zoo.
Let's open the doors to the geometry zoo. I want to walk through these categories because some of them are just wild. Let's start with the most obvious one, the classics.
The conical tips.
The conical tips. In the fine metal catalog, these are styles 01, 02, 03. It's a pencil point. Simple, right?
Deceptively simple. This is where physics kicks in. The angle of that cone is everything.
So let's talk about the sharp ones, the 30-degree cones.
The 30-degree cone is your sniper rifle. It's incredibly aggressive. Because the point is so fine, all the spring force of the probe is concentrated into a microscopic area.
So you use this when you need to pierce through something tough.
Exactly. Heavy layers of contamination or to hit a target that is incredibly small. Like piercing through a layer of varnish or rust. It just punches through.
But I'm guessing I can see the downside.
What do you think it is?
Well, a 30-degree point of copper or steel, it's going to be fragile.
Extremely fragile. That's the trade-off. It wears out fast. It dulls. And worse, it can bend. If it hits the surface at a slight angle, if your machine isn't perfectly aligned, that tip acts like a lever and just snaps.
So it's the glass cannon of probe tips.
That's a perfect way to put it.
So if you need durability, or if your machine is a little wobbly, you widen the angle out.
Right. You go to 60, 90, or even 120 degrees. A 90-degree cone is a tank. It's robust. It can handle high mechanical stress, but
the force is distributed, so it doesn't bite as deep.
Exactly. So it's safer, but maybe less effective on burnt. If you have a heavily oxidized board, a 120-degree cone might just sit on top of the rust.
So you get a fail on the test.
A false fail. Not because the board is bad, but because the tip was too blunt to break through.
I also saw stepped versions of these cones. It looks like a cone sitting on top of a wider cylinder. What's the logic there?
That's mechanical safety. Imagine you have via a small hole in the board. You want the probe to center in that hole, but you don't want it to go all the way through and act like a wedge.
Oh, like splitting a log.
Exactly. If you push a cone too hard into a hole, you can literally split the circuit board layers. The step, that cylinder hits the surface and physically prevents the sharp point from going any deeper.
Smart. It's built-in depth control.
It stabilizes the position and limits the penetration.
Okay, so that's the stabbing approach.
Right.
But what if we can't stab? What if the customer says, no marks allowed?
Right.
The source lists flattened spherical tips. Styles 11, 12, 17.
Now we enter the gentle touch category. You have to think about something called the plowing effect.
Plowing, like on a farm.
Similar idea. If you have a sharp tip and the alignment isn't perfect, see the probe comes down a little sideways, it drags across the metal as it compresses.
It digs a trench.
Digs a trench.
Yeah.
Which is a disaster for something like a consumer USB port or a gold connector that needs to look perfect when you open the box.
Of course.
So you use a flat tip or a spherical tip. A spherical tip is just a round ball, and the source calls this the tolerant shape.
Tolerant of what?
Tolerant of misalignment. Because it's round, if it comes down off angle, it doesn't dig in. It rolls or glides into position.
It minimizes lateral catching.
Very forgiving.
But the trade-off has to be the same as the wide cone.
Yeah.
It can't clean itself.
It's terrible at cleaning. If there is a speck of flux residue or dust on that pad, a round tip will just slide right over it. It won't pierce the film.
So you get an open circuit error on a perfectly good board.
Yes. You trade mechanical safety for higher preparation costs. You have to make sure your boards are squeaky clean before you can use the round tips.
Which brings us to my favorite category.
Yes.
The aggressors. If we have dirt and we can't use a simple sphere, we need something that fights back. We need the crown tips.
Styles 14, 15, 40.
These look like tiny castle towers.
The couronnes, as the French docs call them. These are industry favorites for a reason. You have 3, 4, 6, or even 8 points arranged in a circle around the edge of the tip.
And the source mentions self-cleaning logic.
Yeah.
That phrase stuck with me. How does a piece of metal have logic?
It's structural logic. It's brilliant micromechanics. So because the points are on the edge of the tip, they aren't supported in the center. When that crown hits a flat surface, the force causes those points to splay outward.
Oh, they spread out, like
Yeah.
opening a hand.
A very stiff hand, yeah. They spread and they claw the surface. That scratching action breaks the oxide film or pushes away the dirt. It creates fresh metal-to-metal contact just by the act of compressing.
That is so cool. It's actively digging its own clean spot.
And it has built-in redundancy. This is the key. If you use a single-point cone and it lands on a piece of dust, you fail.
Game over.
Game over. But if you use a 4-point crown and 1 point lands on dust,
The other 3 might still hit clean metal.
and you maintain the connection, the geometry itself provides insurance. It's like having 3 backup plans built into the shape.
But I assume you can't use these on everything. They must leave a mark.
Oh, they scratch. You will see the mark. If you use a sharp 3-point crown on a soft gold pad, you will leave a visible bite. But for soldering pads that are going to be covered anyway, it's the perfect tool.
I saw a variation on this, the serrated tips, style 06.
Right, they look like they have little teeth. Think of those as the heavy-duty scrubbers. Instead of points, you have ridges. The source notes, these are often used when you need to break a surface tension or a layer of varnish, or interestingly, when the pitch, the spacing between test points, is extremely tight.
Why does spacing matter for serration?
Well, sometimes a crown is just too wide. If you have test points that are only fractions of a millimeter apart, you can't fit a big castle tower. A mini serrated tip gives you that multi-point contact, that biting ability, without the width of a full crown.
Makes sense. Okay, let's move to the specialists. These are the shapes that made me stop and check if I was reading the right document.
I know the ones.
First up, concave, styles 05 and 50. It's a cup.
Right. So think about the target again. Not everything is a flat pad. Sometimes you need to test a wire wrap post or a pin that is sticking up from the board.
If you come down with a flat probe on a round pin.
It's like trying to stack 2 marbles. It slides right off. A concave tip is designed to hug the shape. It centers itself.
So it guides itself into place.
It's self-centering geometry.
Okay, that makes sense. Then we have the square lances. Style 33. It sounds like a medieval weapon, and it looks like one.
It does. These have very sharp, defined knife edges. You use these for mechanical anchoring.
Anchoring. Why would we need to anchor?
Sometimes you need the probe to hit a specific spot and not move. If you have a slanted surface or a via hole that isn't quite round, a normal tip might slip or rotate. The sharp edges of the square lance dig in and lock the probe in place.
Oh.
It gives you a very directional, stable contact.
And then the wildest one on the list for me, the rolling ball. Style 90. It's a probe tip that actually rolls.
It is exactly what it sounds like. A captive ball bearing at the tip.
Why? I mean, why would you want your electrical contact to roll away?
Because sometimes the target is moving. Imagine you are testing a battery strip on a conveyor or a connector that slides into place while the test is still running.
Oh, if you used a fixed tip, it would just drag and snap.
It would drag, the friction would snap the probe, or you'd gouge a trench in the product. The rolling ball allows for electrical contact while managing that sliding friction.
That is a very specific solution.
Very niche, but when you need it, there is literally nothing else that works.
Okay, so we've got the zoo. We have cones, spheres, crowns, lances, rolling balls. The big question now is, how do you choose? The expert source from Cotelec lays out a framework, and it says it's not about finding the best tip.
No, and that's the key insight for anyone listening who works in engineering. There is no best. It's about reducing the dominant risk. The selection process is a risk management exercise.
Okay, let's unpack this. Step 1 is understand the target.
Right. You have to look at what you are actually touching. Is it clean? Oxidized? Fragile? If the dominant risk is contamination, if the boards are coming out of a messy process, you cannot choose a flat or spherical tip. You just can't.
You're forced to use something aggressive.
You are forced to use a crown or serrated tip or a sharp cone. You have to prioritize piercing the dirt over saving the surface.
Even if the customer wants a pretty board.
You have to tell the customer, I can give you a pretty board that fails the test or a scratched board that works. Physics dictates the choice. You can't cheat the geometry.
But what if the dominant risk is sensitivity? What if it's that gold connector we talked about?
Then your hands are tied the other way. You have to use a flat, spherical, or maybe a specialized spade tip that distributes the load. You accept that you might have some contact issues if the board is dirty.
So the solution isn't the tip.
No. The solution is to clean the boards better before testing. You trade electrical ease for mechanical safety.
It's a balancing act. Okay, and then step 2 is the mechanical environment.
Yeah.
The bed of nails.
Right. In a vacuum fixture, you might have hundreds, maybe thousands of these probes pushing down at once. The total force is massive. If you use extremely sharp needle-like probes and your alignment is off by just a hair,
They'll just snap.
they'll snap or bend. And a bent probe shorting out against a neighboring component, that's a catastrophe. So if you have a wobbly machine, you need a tougher tip. You switch to a wider angle cone or a step tip to handle the environment.
The source also had this interesting category of risk logic scenarios. We covered dirt and fragility. But what about scenario C, high current?
This is crucial for the EV market, or power electronics. If you were testing a battery management system, you might be pushing 50 or 100 amps through a tiny contact.
Can a little brass needle even handle that?
Not without melting. Here, geometry isn't enough. You need specific materials. The source mentions silver alloy tips. You need internal architecture designed to dissipate heat. If you use a standard steel crown, the resistance is too high.
And what happens?
You might essentially weld the probe to the board.
Which is definitely a fail.
A very expensive fail, yes.
I want to pivot to the consequences. Because the source, particularly the Cotelec document, gets very serious about the cost of being wrong. It's not just about a $5 probe breaking.
No, the probe is cheap. The consequences are systemic. And the most insidious one is the false defect.
Break that down for us.
Okay. Imagine you're manufacturing 10,000 circuit boards a day. You use a flat tip on a slightly oxidized pad. The test fails. The machine screams, "Bad board."
So you pull it off the line?
You send it to a repair station. A skilled technician who is paid a good salary spends 20 minutes analyzing it, looking for the broken chip. They find nothing, they clean the pad, test it again, and it passes.
So the board was fine the whole time. The test was the failure.
Exactly. You have wasted 20 minutes of skilled labor, you've disrupted the production flow, and you've created data pollution. If that happens 50 times a day, your margins just evaporated. All because you chose a flat tip instead of a crown.
And the opposite of that, the past defect.
That's the nightmare scenario. Let's say you use a very sharp crown tip on a delicate copper trace. The crown cuts through the oxide, makes contact, test passes. Green light, or ships. But the crown was too aggressive. It actually cracked the copper trace or thinned it out significantly. The board goes into a car. It works for 3 months. Then vibration and heat finish the job. The trace snaps. The car stops.
And now you have a recall.
You have a recall, a lawsuit, a destroyed reputation, all because the geometry of the tip was too aggressive for the target material.
It's incredible how much responsibility lies on this tiny point. The source also mentions maintenance, which seems mundane, but I guess it's huge.
It is. Premature wear. If you use a sharp needle on a hard surface, the point dulls very quickly. It basically turns into a flat tip. Now you have to stop the production line, open the fixture, and replace the probes.
And downtime is money.
It can be $10,000 an hour in some factories. If choosing a more robust tip, maybe a 60-degree cone instead of 30, can double the lifespan of the probe, you've just saved the company a fortune.
It's amazing how the Cotelec engineers talk about this. They mention their 35 years of experience and really emphasize that on paper isn't enough.
That human element is crucial.
You have to see the workshop.
You have to. You can simulate things in CAD all day. But CAD doesn't know that the cleaning station on the line is skipping a cycle. CAD doesn't know the conveyor belt has a wobble. The real life of the workshop is messy. The probe tip geometry is the tool we use to survive that mess.
It really changes how I look at a circuit board. I mean, every shiny little dot on there was a landing zone for one of these things.
It was. Whether it was a crown clawing into it to clear flux, or a concave cup hugging a pin, or a sphere gently touching down to avoid a scratch, it's a record of a physical interaction.
So what's the final verdict here? For you, the listener, whether you're working in this field or just fascinated about how things are made, what is the big takeaway?
I think the takeaway is that precision is a physical thing. We live in a digital world, right? We think of electronics as code, software, invisible signals. But at the foundational level, reliability is about geometry. It's about a shape.
It's about the tangible world.
It is. It's about choosing the right physical form to bridge the gap between the mechanical chaos of the world, the dirt, the vibration, the misalignment, and the electrical perfection we demand.
It's the 30-degree cone versus the 120-degree cone. It's the decision to scratch and to glide.
And realizing that a simple metal stick is actually a highly engineered, self-cleaning, stress-managing organ of the test system.
I want to leave you with this thought. Next time you pick up your smartphone or start your car or even turn on your coffee maker, think about this. Think about the thousands of tiny microscopic bites that the electronics inside had to endure just to prove they were working.
And realized that if those bites had been made by the wrong shape, if someone had used a flat tip on a dirty pad or a crown tip on a fragile trace, that device might not be working for you right now.
It really is where the metal meets the target. Literally.
Couldn't have said it better.
Thanks for joining us on this deep dive into the microscopic world of test probe tips. It's been a fascinating look at the geometry of quality. We'll see you on the next one.